also remote sensing GIS, one of the leading institutions in the world, which allows most of the Sri Lankans to get involved in researchers and all other new projects involved in this site. So when we come to our today's presenter, Dr. Anmali Bandara, as a student of hers, I would like to give a brief introduction about her as well. She graduated with showing her flying colors from Faculty of Geomatics as well, and completed her master's from Peradeniya University regarding environmental soil sciences. Then he completed her PhD in civil engineering from University of Monash. So her research interests are also involved in these environmental factors like soil science, climate, and also remediation and rehabilitation of soil. So if someone asks me how you connect these remote sensing concepts, GIS concepts, and all these geometric concepts with environmental facts, this might be the Dr. Anmali Bandara might be the person who is perfectly answered that question. So I would like to invite to continue this session without wasting any of your time. Thank you, Dr. Madam. Are you with us?
Yes, thank you, Tilosha. What I want to talk to you about today is the environment of Earth from spatial science perspective, meaning the fact that there is some sort of, you could say, some skepticism about the fact of, spatial science people are not too happy to think of environment as some part that they have to focus upon. So there is kind of like, you sometimes find that why do we need to talk about the environment and the earth from the spatial sciences perspective, because it's such a very scientific science, and that kind of an attitude mainly within our context sometimes. So let's have a look. When we start with the basic definition of an environment, the Merriam-Webster dictionary has this definition that says it's the key word there that I would like to point out is the word complex. So it's a combination of physical, chemical, biotic factors plus the ecological community and also the survival. So lots of things are there. And there is another part onto the environment, which is the social and the cultural conditions, right? So we have a habit of like looking at, the four. Now, I say 4 subsystems here, but sometimes you will find that some people define this as 5 subsystems, given the fact that the atmosphere, the biosphere, the geosphere, or the, it's like the air, the living components, the soil and the ground that you touch, as well as the water. So these are the 4 main components, but because humans play a major role, and also the fact that we have this habit of modifying the environment to suit our needs, our preferences, things like that, we sometimes add an anthrosphere here, that is the human component here. So, but in my case, I have actually put only the 4 cases based on the assumption that the humans are also part of the biosphere. So when it comes to interactions, you can see that now that word complex is very well shown here, given the fact that everyone has interactions with everyone, and it's extremely difficult to isolate one component or one subsystem from the other one and make it independent. So what exactly is spatial science? Now you will have different types of definitions and things that you are used to, but when it comes to spatial science, it is the, we are talking about any data that has a direct or indirect reference to a specific location. So that means you have some sort of a physical feature, but you also have the location of that physical feature so that you can pinpoint that find it, tell someone about it. So this is not only the natural things, the built things, the artificial things, everything is considered under this particular information, right? And it also incorporates that it's also a combination not only of GIS and remote sensing, but also GPS, global positioning systems, surveying, as well as cartography. So surveying, as you all know, is relative positioning, finding the location with respect to some other object, and we are saying that, okay, this particular object is located next to this object in different ways. So, okay, this information also comes under what we call as spatial science, right? So, then the question is, where can we use spatial data in environmental applications? So it's not a case of us telling that you can use environmental sciences and spatial data in this particular place, or saying that, look, this is the only place you can use it. No, there is no such thing. Anywhere, everywhere you can use it, and we are using it. And also the most important thing is we should use it in environmental applications, because it's not something that we should, discard, because it's very important, right? Then the question is, there is something called spatial uncertainty, in the sense that sometimes, when you are doing your undergraduate studies, if you have studied in our faculty, or if you are studying in our faculty, you may have come across the word fuzzy, especially when looking at the work that Dr. Duminda has done, his students have done. So you may have come across this particular word. So it's with that, I would say this spatial uncertainty is the difference between the contents of a spatial database and the corresponding phenomena. So let's talk about it this way. So when you are doing some sort of work, and you take let's say a satellite image, what actually happens is you have a footprint that is let's say maybe 5 meter by 5 meter, and somewhere in one corner you have some specific point of interest. But the thing is, when you look at your spatial data or your footprint, it gives you information for that entire area, the whole square. But in reality, it's just one point. So then you do have a difference between what is there in your database and also the phenomena in the real world. But this is not an error. This is because we expect it. It is inevitable that this kind of difference will exist between the real world and your database. Therefore, we have to understand and appreciate this spatial uncertainty when we use the spatial data. We can't just kind of push it under the carpet or pretend that it's not there, but it's there. So appreciate it, understand it, and then we use it. So that is where we come to the concept of crisp data and fuzzy data. So the when it comes to the crisp data, we are talking about it's either it's there or not there. Okay, so the element is either there or it is not there. But fuzzy, I will show you a diagram in the next slide. But when it comes to fuzzy, what happens is that you have a set of points which can be either fully into one group, partially into one group, and more to another group, but slightly to the first group. So there is kind of a fuzziness, non-crispness that can make it go into either side. So these elements are not given either a 0 or a 1 value, but they range from 0 to 1, that is, can be anything in between. But keep in mind that this is a massive area for research. So this focus on the use of fuzzy set theory to close the gap between mathematical models and the spatial data. So we have a lot of scope. We are doing a lot of research in this area. So when we look at the two data sets, you might think that CRISP data is really good to use and nice. Yes, it's very easy to use. Remember that the error accumulation is comparatively more given the fact that you start the data set with some inherent errors, because when you come to these footprints, not everything is homogeneous. So you have differences within the footprint, but everything is kind of bulked into one category. So you end up with having some sort of errors inside it at the very beginning. But on the other hand, we can get a lot more information from fuzzy data, and we can also expect a better representation of the reality, because it's dealing with not a 0 and a 1 concept, but more information can be derived from there. So this is the diagram I was talking to you about, the fact of crisp and fuzzy data. So if you look at the left hand side, you will see that the data set is exactly into two classes, A1, A2, right? So you don't have any arguments on that. They are in a cluster by itself. But if you go to the image on the right hand side, you will see that the same thing, but some pixels are less towards the group, that particular A1, then more towards that, and you also have some pixels which are kind of coming under both aspects. So you have an overlap, which gives you a little bit more information as well. So therefore, remember that although CRISP data may be the kind of much preferred one, more scope, more information, more research is with fuzzy data. So that is an area. Now the whole purpose of this discussion, the lecture series and this program is actually to talk to you about the potential areas that we are not exploring, or relatively less unexplored and completely unexplored. So this is relatively less unexplored within our context, in our country especially. So remember, try to focus on those things. Now, another key factor, another key problem that we have when it comes to Sri Lanka and spatial data is the resolution, the resolution of the images. Now, I'm not talking about Sentinel, Landsat, the images and the data that you are using at all times, but I'm talking more in terms of the data that you can get from, let's say, for example, something like GRACE, something like SMOS. SMOS is relatively less known here. SMOS stands for Soil Moisture and Ocean Salinity. Although the original design was for, I think, 3 to 5 years, it has celebrated 10 years already in orbit and giving a lot of information. So what I'm trying to say here is that if we take, for example, the SMOS pixel, under ideal conditions, the pixel size is 40 kilometer by 40 kilometer. If you take the GRACE, the gravity satellite, that is about 110 kilometer by 110 kilometer. So when you consider the pixel size and the country's size, it's like, a few pixels can cover the entire country. So we have an issue there. And that is one of the issues that we have to solve using the super resolution. We also have some alternative words you may come across: disaggregation, downscaling, super resolution. All things more or less tell you the same thing. The same thing means that we have a pixel which is of a coarser resolution, which we want to bring down to a very fine spatial resolution, right? So that is why we say super resolution or downscaling. Now the left hand side is actually a 40 by 40 kilometer that has been disaggregated into these little ones are 1 kilometer by 1 kilometer scale. So what you have to remember here is that not only the one data set that you want to disaggregate, in addition to that, you have to have a lot of secondary data into this system to make it into a super resolution image. Now, this is actually some of the work one of my students did a couple of years back. So what he tried to do here is to disaggregate this 110 kilometer by 110 into a 25 kilometer by 25 kilometer pixel size. So he needed to have a lot of secondary data, and you will see that here the selected area is actually Anuradhapura and Dambulla, the area that is considered to be somewhat homogeneous and flat in our country. So I'll talk to you about that in a bit as to why. So this another scenario for research, an area that we have to explore is of course super resolution, because there's no point in calling yourself a remote sensing or a GIS specialist if you do not tap the resources and maximize the use of the data. So manipulating the software doesn't make a person an expert in the area. So that is the difference. You have to know the science, right? Now, now remember I talked about this homogeneity. Sri Lanka, of course, is a tropical island. You know about Sri Lanka better than me. So you must be wondering, why would I say that? It's a tropical island. We have a lot of clouds, high humidity, and we also have a massive amount of water stored in the soil, different types of vegetation, lots of water features. We have coasts, and also the heterogeneous landform. If you are from Sabaragamuwa, then you know that a stone's throw away you have flatlands, and then maybe a couple of kilometers down you can see the mountains. So lots of different features are there, as well as urban areas. So apart from the fact that this slide tells you that Sri Lanka is really beautiful, it also tells you about the potential complexities that the country offers to an expert, a specialist who wants to use spatial data in the Sri Lankan context. Why? Because just now I told you a while ago about this particular area. So I said that this particular person selected a homogeneous area to downscale for the simple reason that if you have this heterogeneity and the heterogeneous landforms, when you consider the secondary data in your super resolution work or downscaling work, there is so much to consider, to understand. So that is, it makes the problem very complex. So on one aspect, one of the shortcomings that Sri Lanka has in using spatial data is because of the complexity in the the landforms and the tropical the tropical characteristics, and the fact that the country is small and the footprints of the spatial data or the satellite borne data are large. So we have a lot of potential for studies with related to disaggregating or downscaling or having super resolution images. Now, keep in mind that those of you who have used satellite images over Sri Lanka, any area, you would have a lot of experience in trying to find an image that has minimum cloud coverage. Why? Because the tropics, tropics have more humidity, more formation of clouds over us. So we are looking at, that is the beauty of the country, but that itself becomes a complexity when we want to utilize the data that is available. So these are actually potential areas that we have to explore and to work together so that the untapped data can be used for our country's different types of developments and activities. So this is what I was talking about. Now, you can use something like a resampling, basic nearest neighbor resampling, to kind of break down this 30 meter by 30 meter into maybe a 5 meter by 5 meter. But what happens here is you're simply still having the same value, even though the size is so sort of like literally larger, right? So that's why we need super resolution, meaning we need to have a lot of secondary data inside this. Another keyword that comes into play when we talk of spatial data and environmental applications is the use of models. Now, models, it's the creation and the use of mathematical models of the environment. But keep in mind that there is no model that can represent the environment or even a minute part of the environment and predict the outcomes with 100% accuracy. So you might be able to get maybe 20, 30, 40, 50% accuracy, but remember that the complexity of the environment stops you from having a perfect model. But don't discard these models saying that they are not representing the environment well and the predictions are not so good, we have so many problems. Never discard them, because a good model can tell you a lot of things that you might never know simply by observing and doing the data collection. So this is one of those evils that you have to work with to get what you want out of the model by understanding the model and understanding the shortcomings of the model. Now, one thing that I have come across, especially within our context, some of the scientists that I have talked with and discussed some work here in Sri Lanka, is that some people do use models, different types of environmental models and agricultural models, things like that. But the thing is, they don't appreciate the model, given the fact that a model is developed to represent something under some different scenarios and limitations. So let's say, for example, that I develop a certain model to represent something that is only for bellyhole lawyer. What happens is someone else can use the model, but you have to keep in mind that the original development was for bellyhole lawyer. Therefore, you have to understand the complexities, the constraints that are in the model and modify it to suit your requirements and your needs, right? So that is one thing that fundamentally we have to understand, that you can't ever blindly use a model that is available in the world. So in the scientific community, if you look at different models, say for example, I use land surface models. When you look at the different parts of the world, they have different models that they are using. They don't use other models simply because the development was focused on that specific area. So if you want to take a model that was developed in Europe for anything to Sri Lankan standards, remember that you have to first figure out whether it's giving us what we want to have within our scenario, our limitations, and our special characteristics, right? Now, that is why we say that this model development is difficult. It's complex, and trying to model the nature is very difficult. And we have to always simplify things. For example, if you have a glass of water and you pour the water onto the soil, when you observe it, you will see that it goes in the XY direction, it goes in the Z direction. Not only that, it is also going in, the in-between directions as well. So you have a solid shape that gets wet at different levels in different levels of wetness. So when you want to model even that tiny little action, you will find that it's very complex. So then we assume and we simplify this and say, okay, there is no lateral movement. We only consider these three movements, something like that. So that is simplification and assumptions, right? So when you use environmental models, bottom line, know the constraints, know the limitations, appreciate the model, and then try to use it for what you want to get out of it. Okay, so but you have to understand the model. Never use the model outcomes without understanding what it's trying to tell you. So the model, you can't be under the model has to be under you, doing what you want it to do. Okay, so another word that comes into this particular concept of environmental modeling is data assimilation. Now, data assimilation is slightly less researched in Sri Lanka and relatively not done much. So I'll give you one excellent example for this. When it comes to the weather predictions, you will see that in certain parts of the world, the weather prediction is really, really good. Like you check the weather forecast before you, decide on what you're going to dress up on that day, what you're going to take, and whether you're going to take an umbrella or not, because they tell you, okay, from 8 to 10 there will be sun, 10 to 12 you will have the wind, and after that it's going to be raining. But at the same time, in certain other parts of the world, when the weather prediction tells you that it's going to rain today, you know that it's going to be a massive sunny day and you can even do your laundry. Okay, so that's the difference between certain parts of predictions, and that is where this concept of data assimilation comes. So data assimilation is actually using real-time observations to correct your forecast. Now, if you look at this particular graph that I have shown you here, the black line is the original forecast. That is, if you don't have any corrections, if you don't feed in any data, that is how your forecast is going to be. And then what happens is you see that these blue stars are the real observations. Now, some of them are significantly above the the forecast, the black line, and some are below, some close to each other. So what happens here is that when it comes to this assimilation, there are lots of assimilation techniques. You put this observation, you put that observation into your forecast, into your model, so that by putting this observation into the model, you kind of pull down your model a little bit towards the reality. So same goes here. And at the same time, because these observations are above your prediction, you kind of lift your prediction to come close to your observations. And then the corrected forecast is, of course, a lot better than your previous forecast, or the one that you have you are going to use, right? So that is not that is another aspect in research that we have to, of course, consider, given the fact that we don't use data assimilation as much as we can. So when it comes to observations, we are not talking about literal, point observations. This can be a time series of data. This can be a time series of spatial data, observations, satellite data as you get it now and as is. Kind of a lot of things are there, right? So we need to consider this aspect of the research as well into our context, right? So we have areas in disaggregation, in data assimilation, in using environmental models. These are things we have not explored that much, but which is in use in the scientific community, which we have to actually seriously consider. So if I take on some examples, now I will be taking some examples from what has been done by different people. So that is not the only things, and they are not the best things or the worst things. Okay, they're just examples for you to get an idea of what can be done with spatial science in terms of or the context of environmental application. So this is actually part of my work, or you could say that it was the last part of my work. Now, spatial data, you have a very good idea about what spatial data is. Now, if you look at this, this is actually a soil parameter. A hydraulic parameter is estimated and taken out, extracted by using spatial science or satellite data. So in my case, I use the soil moisture and ocean salinity satellite information to extract these hydraulic properties, which are not directly linked to the satellite data, but indirectly linked. At the same time, surface soil moisture, of course, you can get to about 5 centimeters at maximum. But when it comes to the subsurface or anything below 10 centimeters, that's not possible for you to obtain directly through satellite data. So for that, we need what we know as environmental models. So indirectly, we can get. So this actually shows you that the hydraulic properties, as well as in technical terms we call this the root zone soil moisture, these can be extracted and obtained in different ways using spatial science in environmental applications. So these are things that we have a lot of potential for. Now remember that in this also, if we are to use a model that we want to use for the Sri Lankan context, we have to appreciate the Sri Lankan complexity and then find out what is the most appropriate and the corrections and the modifications. Another example, because we were talking about 4 different concept subsystems, the soil, the air, the water and the living things. So we can also talk about this. Now they have used GRACE is, most of you are aware of GRACE as a gravity measuring satellite or extracting gravity, but it's also able to give you the terrestrial water storage, which is very important. Now this particular work has looked at GRACE plus a different, using different models, TWS, they have found or they have predicted the terrestrial water storage and obtained the terrestrial water storage. So if you look at these two lines, you can see that there is kind of a good match at one point, some differences. So this is, it's not within my context to talk to you about the whys and hows, but just to show you that we can do this kind of work. And another, so snow is not very familiar to us because we are tropical, but you can use this spatial data to calculate and to observe and obtain the snow grain radius. And also when you just look at this particular plot, you can see that there is a very good match between what the sensors have sensed and given out as well as the measurements. So adding on to this, there are some other research work that they do on snow, different the melting and the freezing or the thawing of the snow, and how much snow is lost during the spring and the summer and how much is added. So these kind of research are also there with spatial data using different types of spaceborne and airborne data. Right, so I didn't bring those examples here because we actually don't have it for us at the time being. Now another part is water, and this is very less researched in our country, the use of satellite data in ocean studies, in freshwater studies, things like that. So these are both images that I took from the ocean salinity satellite. So this is just a very direct, straightforward ocean salinity map for the year of 2011, the sea surface salinity and so soil moisture and sea surface salinity. But this is very recent actually. This shows you the wind speed over the ocean for a particular storm. So this kind of information, and they have given you the different, these are the different speed limits of the wind. So this kind of information also we can obtain from spatial data or from satellite borne platforms, right? So for the people who are interested in hydrography, people who are interested in freshwater research, try to utilize this aspect of the spatial science in your research, because there is so much data, so many problems, but so little work done. And of course, this is another example for, this is freshwater studies in terms of sedimentation, reservoir sedimentation. So what they have done is using satellite-borne data to demarcate not the volume, actually the XY spread of the water and how it changes. And this is also about the sediment accumulation of a particular location. So you can see that now when it comes to our country, we have so many rivers and we have so many problems associated with sediments, because you hear that the volume of a lake is going down, the volume of the river is going down, there are so many flash floods. So everyone knows that a flash flood occurs because the river or the water body is incapable of absorbing all the water that flows into it. So one of the main reasons for that is the siltation or the sedimentation, thereby reducing the volume of the water body. So of course we have a severe problem in Sri Lanka with sediments. So why that we are not using satellite data and other information to estimate the sedimentation and to track the sediments, model them? That's a question that I'm always having as to why we are not doing it when we have the technology and when we have the problem looming in front of us. So I think I'm hoping that someone might be interested in this area as well. Now, of course, personally, I really like this image. It's very nicely presented. Now, this is another aspect of the subsystem of the Earth, forest fires. What they have done here is, what they have shown is, in different colors, you have the different levels or the layers that the smoke has come from the forest fire a few days, like in this case, the 4th day before coming to this area and the 5th day before coming to the area. So you have the trajectories. The whole work was done using spaceborne data. So that is just one example of forest fires, and this is actually a tornado. If you look into this particular paper for some kind of a reason, you will see that they have even shown the direction that the trees have fallen. That is how much spaceborne data can be utilized for environmental applications. Not just simply to say that there is this kind of a problem, there is a disaster happening. No, they have tracked the disaster, the path of the disaster, how it has happened, which direction the wind has gone. So all these are coming from spatial science, spaceborne data, airborne data. So use this data very kind of, in a very nice manner, and you will have an unbelievable amount of information. Now, because I can't show you the this was a GIF. So back to this. This is again a forest fire in the sense the Amazon area. So you can see 2013, 15, 17 and 18 how much the deforestation has happened. So this is just a kind of a brief overview about what has happened, but think about how you can use this kind of information, this kind of data for different things, for different research activities, to answer questions that we have in the country, things that are important, right? So I also want to point out now, since we are talking about this, this particular program is by the SEDS Sabra. So the Space Apps Challenge by the NASA is giving you some really nice questions. They are asking in one aspect resilience studies. Then helping hands, more society related questions are being asked to be answered, right? So atmosphere related research questions. So these are all about utilizing different data from different spaceborne or airborne aspects. Say if you go with SEDS challenge, space apps thing, they are asking you to utilize NASA, ESA, JAXA, all the data that is available you can use. So think, why would they ask you to answer a question like, something related to the society if we can't use spatial data? So that has to tell you, that has to kind of, you have to understand that this is not about just mathematics or biological sciences. This is about everything in the environment, including people and animals. So I did not discuss about, I did not bring examples about landslide studies, these classification studies. These are very commonly done in our country, but they are also at very kind of not utilizing all the data, you could say. And another example, this was, I think, a 2019 project, the Space Apps Challenge. In Philippines, they are going to, the proposal was to utilize most of the spaceborne data to have an advanced early dengue prediction and exploration service. Dengue is a problem in our country as well. So this is using the scientific knowledge, the technical knowledge, the know-how to solve a problem that is very social society based, right? And these are from the 2018 exam challenge. So, we are looking at health aspects and displacement of people, real settlement, refugees, things like that. So imagine and try to kind of link these kinds of problems with the technology and the technical know-how. That is the real challenge when it comes to research. Not kind of going forward with what you know, but trying to incorporate what you know into solving a burning issue in the environment in the country. So another set of examples, this is actually more towards the ecology part. So they are trying to find the migratory travels of animals and different invasive plants, what are important, what are not important. So these are the aspects that we usually do not straight away associate with spaceborne data or satellite data or GIS or with remote sensing. So these are the things that you have got to incorporate into the the research component, right? So this actually, I just wanted to highlight to you how hard these guys, Tilosha, Anupa, and especially, those three, Vishwajit, Kavinda, they are working. So this was their challenge. They wanted to do this SEDS Sabra and submitted a project. So this is their attempt, and I must say that the reason I put it forward is because it's really good and I want to say thanks. So that ends my discussion, and so the official thanks are there, but in addition to that, I want to appreciate Dominda for actually believing in me, and Anupa for forever bothering until we agreed and did this program. So without Anupa, Tilosha and Kavinda, I don't think we would have this program. So thank you very much. You can ask anything. I would rather you ask questions because it's easier to answer that way. Thanks. So, any questions? No questions.
I've got a question, madam.
Yes.
So you have mentioned about atmospheric data modeling and weather prediction, and we are facing some sort of a problem in prediction for Sri Lanka. So you mentioned that it's purely due to the data assimilation, or I'm wondering, is it due to the data assimilation, or is it due to the data model that we are using?
Actually, to answer that question, there are several reasons for that, Darshana. One of the key problems is that data assimilation. I'm actually not very well conversant about how they assimilate the data, whether they use real-time data or whether there is a lag in the data that they put into the model. That is one reason. Another reason is that when you do weather predictions, we have to have a combination of different models to kind of it's not just a case of just atmospheric models. You have to have land surface models, vegetation, things like that. All things together is what gives you the weather prediction. So if you have mainly your land surface model is not giving you a correct soil moisture output, that can have a massively negative impact on the weather prediction. So most people are not aware of the fact of soil moisture impacting the weather prediction that much, but that is one of the key issues. So I would say that maybe it could be a problem associated with the combination of models that we are using in Sri Lanka, or it could be one specific model is either underestimating something or overestimating something. So then the final prediction would be wrong. And also this data assimilation component should also come into being. Like, real states, if we can get the satellite data, what is happening now, and update your model, then within an hour, the prediction will be a very close match to the reality. So lots of things are there.
Okay, thank you very much, madam.
You're welcome.
Madam, moving on to another application of forestry. In forestry, tree mortality is a high impact towards the global scale. So in that, in terms of that, we have to cooperate with so many models like prediction models and weather and lots of things. So when we are going to cope up with all those models, will the results contaminate with so many errors, or some models that we have to implement will be global scale? So what sort of issues that may have implemented towards?
Well, the first part is that yes, you will always have, what you get as a prediction is not what you want or what you expect. Okay, so that discrepancy is always there. That has to be there anyway, because you know that each model has shortcomings inherent to it. So when you have a lot of such models working together, you actually expect something, not what you want at the end of the day. But having said that, what you have to understand is that combining all these models with shortcomings will give you information and answers to questions that otherwise you would never have known. Okay, so it's kind of a balance between how much we should take from that and how much we have to filter out. So the problem is we don't have anything that is perfect, and therefore the outcome will be incorrect, and that could result with how much of errors you started with, but still you get some sort of information. So you have to understand the models to deal with the final product. Did I make it clear?
Yes, but madam, when we go forward towards the forest application, most of the moist-based forest applications are very low in their publishing and everything. It's because of there are so many barriers for that. For example, if we take Landsat images, it will be disturbed by clouds, as for example. So we have to bias towards the models. So when we take the global scale models, some of the models are done according to the specific something like particular coordinate system, like likewise something like common things. So when we are going to implement towards our project, then according to the continent, it may varies the projection system. For example, the projection system, the coordinate system will be varies from continent to continent. So how can we eliminate this problem?
One thing is that when it comes to most of these models, they are not black boxes, you know, they are codes. So one of the ways that we actually encourage people to use an existing model is to take it apart and put it together with your own parameters and your own constraints. Say, for example, there is a very well developed and very extensively used model looking at a certain forest, which is not, let's say it's not tropical, okay, something to do with pines, what we call as evergreen forests. So if you use that model onto tropical forest, of course you expect a lot of problems there. So the best thing is you have to modify that, putting in your differences and kind of you know, adjusting the codes and recoding certain aspects and putting different conditions to suit your own scenario. So that is one of the, you know, that is probably the best way for you to use an existing model.
Okay.
Okay.
Then, madam, will the accuracy will be affected by when we are going to decode the existing code itself?
No. It's usually they have, let's say now, most of these hydrology people, they like to use Fortran for whatever reason, I don't know. So the code is there, and
Yes.
you just have to go through, because you see, one of the examples is that you know, certain limitations are there. You know, when you feed in a parameter, they tell you that 0 to 10 you can feed in this parameter, but sometimes inside the code they have put a constraint saying that for this particular area X, this value can't go beyond 8, therefore don't accept anything beyond 8. Okay, so there is a constraint there. Now those kinds of things have to be changed and looked into when you're doing the modification. So it's actually these models are open to the community to change and to adapt and recode, because that's how research is done and the model gets developed.
Yeah, thank you, madam. I got the answer. And thank you very much for your nice presentations and description. Thank you very much.
So
Hi, Anne-Marie. Thank you for your presentation. It was a pleasure listening to you. I know that you have been working much in soil and water. So these days, it has come to a level that we understand soil and soil moisture are much more important for our work. Is not only in forest and agricultural studies, but also in the case of construction and engineering, it has become very important to understand the soil properties. And I have heard the term that the wealth of a country is its soil. So do we have a comprehensive soil map for Sri Lanka, or are we doing, do we really know about all the soil types of Sri Lanka? How long it will take for us to, is there any projects going on to map the whole country for the different soil types, or anything in that direction you know about?
So starting from, let's say, the bottom up, Peradeniya soil science people are the key people for soil science in Sri Lanka. So they had a project called Sri Can Sol, I think Sri Lanka, Canada, kind of a huge project. And they, with that project, they have done a lot of work in the country about soil, you know, profile, not only the surface, but into profiles as well. So they have published actually 3 books. One, the soils of the wet zone, soils of the dry zone, and the soils of the intermediate zone. So that is the extensive, or what we say, the most detailed information we have in Sri Lanka about our soils. But there is a fundamental problem with soils. It's not actually a fundamental problem. It's a fundamentally nice thing about soils, is that no matter how hard you try to categorize, it's impossible. Because within 2 centimeters, you can have drastically different soil characteristics. So, but still, for the country, using those data that they have collected, that is real field data, we actually have interpolated maps. So that is what we can use in our day-to-day work if we want to do it. But if you want to study an area and there is a fine scale is needed, of course, I wouldn't say that that is the best way, because that is significantly cost. But again, we have global soil maps that is even coarser. So it's a, yeah.
Thank you, Ranmali. It was a pleasure listening to you. Thank you very much.
Thank you. No more questions. So, Anup, shall we wrap up then? Anup Otilosha?
I think Madam will be available through email if there are any more doubts. So you
Yes.
can contact her for sure. So thank you, Madam, for sharing your knowledge with us. So this is a great opportunity for, as pneumatic students, we have least an idea about these concepts, but there are so many other fellow settlers who are even interested in these subjects. They have no chance to study these concepts until they follow a master's degree or something like that. So I think it's our duty to share these knowledges with other universities as well. I think we really appreciate your concern in helping us. Really, you and both Dr. Valikan and you advised and consoled us throughout this conducting this webinar series. Really appreciate your help, madam. So next webinar session where will be conducted on next Monday. So if there are any doubts on these topics, you can contact these two lecturers through emails. They will be very happy to help you and solve your problems. So if there are no more questions, let's wrap up this session. Thank you all for participating. And if you want to have a look at this session again, it will be available on YouTube as well. We will share relevant links with you through our social media. So thank you, madam, again. Thank you, you, Dr. Varikanda, for your help and guidance as well. So, and also special thanks for you for participating. I think almost 120 participants were here, and yesterday also over 100 participants. So we didn't expect such a high participants from throughout from worldwide. Actually, you know, some participants are from foreign countries, so we are really amazed with your participants. So thank you all for your contribution. So let's meet again from next session. So thank you.
Thank you very much.